Hi, and welcome to this video on how to accelerate your static analysis in nTop with Sileom Simulate, our meshless GPU-accelerated static solver. My name's Justin, and I'm going to give you an overview of how Sileom Simulate can deliver results fast enough to allow early design insights and rapid iteration. Sileom Simulate is our connector plugin for nTop. It provides new blocks for defining boundary conditions, simulation settings, and for executing and visualizing the static analysis results. These tools allow you to accelerate your static analysis workflow in nTop in two ways. First, by bypassing the meshing bottleneck. Generating a body-fitted mesh is slow, error-prone, and fragile. Sileom Simulate uses an immersed boundary technique to work directly with the geometry, skipping this costly meshing step. Secondly, by taking advantage of GPU acceleration, Sileom Simulate is able to leverage significant parallel execution of its solver routines. And you're not locked into a particular vendor. It works on almost all Direct3D12 capable GPUs. Let's take a look at an example of how powerful these techniques can be. In this case, we'll look at a wing section, which has been hollowed out and filled with a lattice structure. Building a body-fitted mesh with geometry like this can take several hours on a typical desktop workstation. But with Sileom Simulate, this can be done in minutes. And it's easy to set up. Let's take a look. Here, you can see the outer wing section that we're starting with. We'll use the section cut viewer to see the lattice structure we've added to the interior in order to reduce weight and maintain stiffness. This latticing adds a degree of geometric complexity which makes meshing and thus the static analysis difficult. So let's see how we can use Sileom Simulate to solve this without building this mesh. The first step is to specify the boundary conditions. Now I'll show the boundaries briefly here, but for details on how Sileom Simulate specifies boundaries, please see the documentation link in the description. Now boundaries in Sileom Simulate are provided by supplementary implicit bodies, whose intersection represents the surface upon which the boundary condition is to be applied. So we'll assume a distributed lift force, shown here in pink, on the lower surface of the wing, and we'll assume a fixed region near the near side, shown here in blue. Now let's go ahead and execute our static analysis block. Sileom Simulate will give the current progress estimate and some more information about the state of the analysis. Let's take a closer look. On the left, we have an indication of the current phase of the simulation. Right now, it is resolving the regions of the grid in which the boundary of the domain is immersed. On the right, we have information regarding the GPU we are running on, in this case, an AMD Radeon 7900 XTX. And we also have the amount of available VRAM on our GPU. This is important because it gives an indication of how large a model we can execute on this GPU. And once this boundary resolution is complete, we can see how big the model we're running is, about 2.1 million degrees of freedom. And this is consuming about 12 gigabytes of memory, well underneath our 24 gigabyte maximum. Now, while this is running, let's go ahead and take a look at some of the custom Sileom Simulate blocks. Again, for more details, please see the documentation link in the description. So as you can see, first, we pass the boundary implicit bodies into these boundary condition blocks, a displacement restraint on the side face, and a force on the lower face. And next, we have blocks which control various settings for the simulation, such as element size, refinement levels, approximation order, and material properties. And our execution block takes our boundary conditions, executes the simulation, then generates and loads the visualization into nTop. Let's check back in on our simulation. It's currently generating its solution and making good progress, so it should be complete soon. Let's wait. So now it's finished generating the solution and it's preparing the visualization results. When complete, these will be loaded into nTop to allow the user to see the typical stress and displacement fields. Let's take a look. Now with the results generated and imported, we can take a look at our stress and displacement, and we can see the effect of the lattice regions on the stress concentrations. Now, for comparison, we also have the results of a native nTop static analysis. This was performed by generating an FE volume mesh with the same element edge size as the cell size used in Sileom Simulate. This resulted in a body-fitted model with about 2.6 million degrees of freedom. And in this case, we have very good agreement on maximum end displacement, within less than a percentage of each other. And the maximum stress is in agreement to about 13%. Furthermore, we can look at the runtimes for each case. For Sileom Simulate, we can see the execution time is about 321 seconds. And for the native nTop case, the FE mesh block alone takes over 20,000 seconds, a reduction from about 5 hours to about 5 minutes. And these performance improvements persist as the meshing complexity increases. Here's a collection of performance comparisons expressed as speed-up multiple for a variety of lattice cell sizes representing denser lattice patterns and sparser patterns. Also included is a hollow shell with no infill, which should represent a relatively simpler case to mesh. And in these cases, we've relaxed the requirement that the fitted mesh have elements of similar size to the meshless model. Thus, these nTop models run fewer degrees of freedom than Sileom Simulate does. As you can see, the speedup is still quite significant, with larger improvements for more densely latticed patterns. Thanks again for watching. The notebook used here is available at the link in the description, as well as links to Sileom Simulate documentation and how to download a free trial of Sileom Simulate.